So I'll just try to give you a brief revision about what we have learned, and then along with that, we'll try to understand some of the current equations that are available within the MOSFETs. So basically, when we try to understand, when we say that there is a flow of current, how exactly that current looks, what is the expressions that current will have. And we have also seen that there are different region of operations. So exactly how my current is going to behave in both the regions. So let us try to get into a little bit of background what we did. So if you see over here, this is basically the structure of MOSFET, and we have seen that there is an P substrate. Now here I am considering simple NMOS basically, and where you can see there's a channel formation between the source and drain. And if you observe, there is a formation of an inbuilt PN junction diode, which is always a reverse biased kind of thing, which is going to ensure there is no current flowing between these two regions. Because in my MOSFET, when I say there is a flow of current, that current flow has to happen between source and drain only. There shouldn't be any current flowing inside the MOSFET anywhere else apart from the channel. So that is one thing you should remember. If at all something of that kind happens, then that means that MOSFET is about to get damaged or it has been damaged. That is basically a kind of structure my MOSFET will have. And this is the reason why I am showing this internal inbuilt structure of PN junction diode, and they prevent current conduction from drain to source when a voltage VDS is being applied. Because if you see over here, whenever we apply a kind of voltage over here when we apply any voltage between these two terminals over here and a voltage here, these by default make them a reverse bias kind of thing, because like I told, this body is connected to the negative potential or it is grounded. So basically my P side is at lower potential, and if that happens, my this particular PN junction will be reverse biased, and here is also my N side of my PN junction will be at a higher potential. That means this particular PN junction is also reverse biased. So basically, this is going to ensure there is no conduction that is happening within the MOSFET. Now, these things are very important ideally when we uh, when we make any progressions in our career. So these kind of small things that are very important, that will fetch you good inputs whenever you attend any exams, any competitive exams, or you go for any interviews. Fine. Now, this is what we have seen. Some animation I have done. So this is basically how the channel is created when I'm applying some VGS. And what is going to happen initially, it is going to pull all the positive charges towards the substrate, or towards the body. And the moment this happens, there is a depletion region is going to create, because if you see over here, there is an no there is particularly there is nothing is being present over here. So that is basically, if you see here in this region, no charges are present, because all the positive charges that are present within the p-type substrate are being pushed down. So that is basically is going to happen whenever we apply the initial voltage, and then immediately after that, when we ensure that VGS is retained, it is going to attract all the negative charges just beneath the oxide layer, and this is how kind of bound charges that come and get placed beneath the oxide layer, and this is how I say there is a formation of a channel. And then upon, see, this is how basically the channel forms. And then next is when we apply certain voltage of VDS, then there is a flow of current. So this is basically how exactly my channel looks. Now this entire thing is made up of N type of material. So this is basically, I can say, this particular kind of MOSFET as an enhancement type MOSFET. Why an enhancement type MOSFET? Because out of nowhere, the electrons or the charges have enhanced themselves in creating a particular region beneath the oxide layer, and as a result of which the channel has been enhanced. So basically this is known as enhancement type MOSFET. Like I was telling in my earlier session, there are two particular type of MOSFETs. This is one particular thing. Now, if I just try to ensure this channel is predefined, if suppose, let's say, I create a particular MOSFET where this channel is built before I apply any VGS, such kind of MOSFETs are known as your depletion kind of MOSFETs or depletion type of MOSFET. That means the basic difference between enhancement and depletion over here would be enhancement type of MOSFET would be ensuring the formation of channel once you apply VGS. So basically here VGS should be applied, whereas for your depletion kind of MOSFET, you just do not apply any VGS. By default, the channel will be formed. I mean, by default, channel will be present the moment it is manufactured, and you apply VGS just to enhance or just to reduce the width of the channel or increase the width of the channel. Just to control the width of the channel, you apply the VGS. But otherwise, in the depletion kind of MOSFET, there will be always a default kind of channel that is being formed. So this is basically going to create a path, and that's how the current starts to flow. Yeah. Now, certain equations that one has to remember, like I was talking about the threshold voltage. So it is basically a minimum value of VGS that is required to form a conducting channel between the drain and source. And its typical value would be somewhere around 0.3 to 0.6 times of VDC. VDC here indicates my supply. So if I consider supply as 1 volt, somewhere around 0.3 to 0.6 times 1, which would be again 0.6. So in that range, it would be typically be there, and it is not a fixed value that comes during fabrication. It is, you can change the threshold voltage as per your convenience based on when you want to ensure the channel is going to conduct itself. So that's how my threshold voltage is reflected over here. And when we say there is an whenever we apply a VGS, there is an field creation happening. That is basically when we apply VGS, electric field develops between the gate and the channel, and this is going to enhance the conductivity within the channel, and that's how we say it's a field effect in nature. And here basically the dielectric will be made up of SiO2, that is silicon dioxide will be my oxide layer that we are going to use as a dielectric just before the metallic conduction and the p substrate. So there, whatever you see the oxide layer, that is basically a silicon dioxide. Of course, there are multiple oxides that we can use. This is one of the most common silicon dioxide as a dielectric to be used. Now, when we try to ensure the channel is created, so basically whenever we say that at a particular value of VGS, which is nothing but we say here as a threshold voltage, the channel is being formed, and that particular voltage, that is the difference between the VGS and VT. Like for example, if we assume if VT is, let's say that 0.5 volts, that means at exactly 0.5 volts channel is going to be formed, but I apply VGS till 1 volt, then the difference between VGS and VT, which happens to be zero point 0.5, that particular zero point 0.5 is known as your overdrive voltage, or basically an effective voltage that is basically making your entire formation of channel and ensuring the current flow happens between source and drain. So this is one of the most important term that we should remember, the overdrive voltage. It is basically the difference between the applied VGS and VT that one has to remember. Now, at the same time, there is one more important thing that happens. So if we observe here, whenever we talk about a cross-sectional view of a MOSFET, we say that there is an oxide layer over here, and on top of that there will be metallic connection, and beneath that there will be a channel being formed. So assuming this as an NMOS, so you have applied a positive voltage, and here the negative charges are being accumulated over here, and there is a capacitance that develops here, and that capacitance is basically your oxide capacitance, or in fact I can say that there will be an oxide which is present over here, and if I want to ensure what is the capacitance of that oxide, I say that as C ox, which is represented by epsilon ox by T ox, where epsilon ox is a permittivity of SiO2 and T ox is the thickness. So basically the C ox, so whatever the oxide we are going to use, that oxide also will have certain capacitance which we denoted by the term C ox. Now why I'm going to tell all these things, because if I know all these terms, then only I'll be able to get an input on how exactly my current equation would look. So that is basically the intention over here. So let's try to go ahead further. Now here what I'm telling, whenever a channel is being created, the basically when I apply certain VGS which is more than VT, or by applying certain overdrive voltage, now henceforth I do not talk in terms of VGS, rather I talk in terms of VGS minus VT, which is nothing but my overdrive voltage. Because always remember, the threshold voltage is the bare minimum voltage that is required to form the channel. I don't always apply a voltage at exactly VT. I apply certain voltage more than VT, which is my VGS. And the difference of this would be your VOV. So whenever we apply certain VOV, there is a formation of channel. And how we can ensure the value or the entire magnitude of the current. So basically I can say the magnitude of the current is nothing but the flow of charges, and I can express my flow of charges as Q equal to CV, and this is basically my equation of my charges. So whenever the charges, when they start to move, I say that the current is getting flowing. So that means if I try to understand the magnitude of my charges, then I can easily quantify the amount of current. So that means I can represent Q equal to CV. Now here V here represents my overdrive voltage, and C represents the oxide capacitance, C ox over here, VOV is my voltage, and this CV is flowing, or this charge is flowing in an area represented by W times L, because the channel has got a certain width, certain length that denotes the area of the channel, and within this area the entire charge movement is happening, denoted by Q equal to CV times WL. So that is how the magnitude of electron charge represents. So that means now we have understood there is a magnitude of charges represented by Cox WL times VOV, and VOV itself is nothing but the overdrive voltage, which is the difference between VGS and VT. And then there is a width and length of the channel that is getting represented, basically the area of the channel. Now by clubbing all these things, we can be ensuring to denote a particular expression which can be written something like this. Now if you see, the drain current can be represented in a simplified manner without having to know and the entire derivation. So here we are not interested in understanding how to derive it. Of course, that is there. I can refer the Razavi textbook to understand the derivation of that. But I can represent this entire theoretical aspect and can club all these contents into ID. So which is represented as charge per unit length of N channel, that is C ox W times VOV C. I am just taking out the uh, L portion over here. So here I'm representing that particular thing. And what is this? This is the electron drift that I'm representing. So this is basically mu1 is nothing but your mobility. VDS is nothing but the applied drain to source voltage per length. So mu1 times VDS by L, and Cox W times VOV. And if I club all these things and try to rearrange this entire equation, I can say that this is how my entire equation is going to represented, and ID can be represented as mu n Cox W by L VOV times VDS. So this can be further simplified in terms of VGS as mu n Cox W by L VGS minus VT times VDS. So this is basically for a small value of VDS. So all these entire equation I'm writing it for a small value of VDS. So of course, if I try to derive it, it would be something like this: 1 by 2 times VDS square. So this would be basically how my equation looks. But because I'm talking in terms of a small value of VDS, when I say a small value of VDS, the see if VDS is itself very small, then the square of that would be even very small, and as a result of which I can ignore this content, the last component of my equation, and I can represent my ID for a small value of VDS, something like this, which is ID equal to mu and C of W by L VGS minus VT times VDS. Now this is basically the equation of drain current with the help of a representing a for a small value of VDS. Now, based on this particular equation, I'm going to take out one particular important aspect, that is, if I bring this VDS down over here, so can I represent ID by VDS something like this is equal to mu and C ox W by L VGS minus VT. So if I just take the reciprocal of that, that is VDS by ID, that means I can say it is going to represent as a resistance. That means the resistance that is being offered by the channel when it is having a smaller value of VDS can be given by 1 upon mu and C ox WL times VOV. And why I am considering a small value of VDS? Because like I told, when I try to plot a graph of VDS versus ID, you get a graph something like this. And here you depict two regions. One is for a VDS greater than this particular value, VD sat, and for a particular value of VDS which is lesser than this. So for all the smaller value of VDS, you can represent there is a small resistance that is being offered by the channel when the value of VDS is very, very small. Or I can say there is a small resistance RDS that comes into picture in my triode region of operation. And the same MOSFET equation entirely behaves as a constant current source, because after a particular value of VD sat, my current is going to remain as a constant. So in the saturation region, so my MOSFET is going to behave as a constant current source. So that means I can be seeing the two different behavior of my MOSFET just before entering the saturation region, or another thing is before the saturation region, or that is in the triode region. So in the triode region, my MOSFET is going to behave as a small resistance with a value 1 upon mu and C ox W by L times VOV. And after a particular value of VDS, or after a particular a point of voltage where it is going to enter into the saturation region, I can say that MOSFET is going to behave as a constant current source. And when we saw the entire operation of MOSFET, we saw that it was also behaving like a simple capacitance also. So this is how my MOSFET is going to behave like a simple capacitor, resistor, or a constant current source under different conditions. And this is how I can utilize them into various parameters. So this is basically how I can say that the equation of RDS. Now, if I just try to relate this RDS, on which all parameters is going to depend, it depends on mu n times Cox, which we usually call it as process transconductance parameters. More onto this, I'll deal it in the subsequent session, but the naming convention, that please you try to remember this. So RDS is basically mu n times Cox, and W by L is basically we usually call it as a aspect ratio. So henceforth, I do not be calling it as a W by L ratio. I can call it as an aspect ratio. So that's what has been mentioned over here. And it also depends on the overdrive voltage, which is nothing but the difference between VGS minus VT. So that's how you can see that there is a dependence of RDS. Now, let's try to understand how my equation is going to look when I try to increase the VDS. So like I told, when I increase the VDS, basically what is going to happen, if you see this graph, which I just showed you here, if I keep on increasing the VDS, the current already has reached the saturation. So there is no further increase in the current, and my MOSFET will be retained in the saturation region, and as a result, the current continues to remain constant. So that's basically is going to happen when we keep on increasing the VDS. There is no more um, um, incremental thing that is going to happen with respect to current. So ID is going to remain almost constant. Now, before I reach into this particular equation where you see the drain current equation, like here, like there are two current equations I have written over here. So let's try to bifurcate my entire channel construction and its voltage distribution within the channel, how exactly it looks. Now, like I told, when there is a channel created and my MOSFET enters into saturation region, there is a pinch off that is going to happen. This is what basically we have seen. So in the last session, we saw that in an N plus region, this is getting more and more positive, and the P substrate is getting more and more negative, and as a result there is a formation of a depletion region over here, just like it is going to behave like a simple PN junction diode, and as a result the channel over here would be eaten up by the depletion region or the reverse biased PN junction region, and as a result my channel would look something like this, and that's what has been shown over here in figure number 3b. So this is basically my channel looks. And now if I try to understand the voltage distribution, so in a simple and in a quick manner, let's try to distribute how the voltage looks. Now, if I just try to figure out the voltage at exactly the source node and the voltage at exactly the drain node, and what is the average voltage that is going to be reflected at the mid of the channel, let's try to figure out. Now, because I apply initial voltage and the channel is being formed, I can say that whenever there is a formation of channel, it is the overdrive voltage or it is the VGS minus VT voltage that has been applied, and because of which the channel has been formed. So I can consider at the source node, the voltage would be exactly equal to VGS minus VT, which is VOV. But the same VGS minus VT won't be remaining same, because as the channel increases and as the MOSFET reaches the saturation region, this is going to get decreased, because if you see the channel is getting tapered. And how much decremental it is going to happen? Sorry. So it is going to basically decrease by an amount of applied VDS. So because see, the moment you start applying some VDS over here, that's when the reverse biasing happens, and that's when the channel gets tapered over here. So that means whatever the VOB was there initially, that is nothing but now it will be VOB minus VDS. So at this drain end, it will be VOB minus VDS, and the source end, it will be VOB. And if I just consider a simple averaging, it will be exactly half of VDS over here. Here it will be total VDS, and at this point of time there will be no VDS, because here there is no VDS being applied. So at this drain node there is a VDS being applied, and at the mid node I can simply just consider there is a 1 by 2 times of VDS. So if I say that at the drain node the voltage or the overall voltage is VOV minus VDS, then at the middle point of the channel I can say that it is exactly VOV minus half times of VDS. That means if I try to represent this further, VOV is nothing but VGS minus VT minus half times VDS. So in my entire channel, the average voltage drop at exactly mid of the channel, I can take it as VGS minus VT minus 1 by 2 times of VDS. So that's the reason this half VDS terms will come into picture, and this is how the entire voltage equation that was I took over here. So this is the equation. If I just go back into the this particular equation of the RDS, ID is equal to mu and C ox W by L VOV times VDS. So this equation I'm rewriting over here. So if I try to rewrite, see, mu and C ox W by L, this is this what was this? VOV times VDS. So now VOV is represented by the term VOV minus half VDS. Why VOV times half VDS? Because here we just now saw that the voltage drop at exactly middle of the channel will be VOV minus half times of VDS. So if I try to do this and try to simplify VOV, if I replace that VOV with VGS minus VT, I'm going to get all the entire values. And if I further simplify, if you can see, this is what exactly you can arrive at two different equations. This is for a particular value of VDS lesser than VOV. Again, you can replace VOV with VGS minus VT. So that would do that. So see again, let me try to write that. So this, if I rewrite, is VGS minus VT and half VDS times VDS. So if I multiply, it will be half VDS square, and this will be VGS minus VT times VDS. So it is going to come down to the same equation of the drain current equation in your triode region. So basically, when I say it is a triode region, when VDS is less than VGS minus VT, which otherwise means this is in the saturation region. So I can replace again VOV with VGS minus VT square. So this is basically triode region versus saturation region drain current equations. And if you see that in your triode region, the drain current is dependent on your VDS, like here. See, your drain current was dependent on VDS, but in saturation region, your drain current doesn't depend on VDS, because like I told, even though you increase VDS, there is no further increase in the current. And that's the reason, if you see in the equation, there is no term involved with respect to VDS. So ideally speaking, this is the scenario. Practically, there is some sort of involvement, but let us not get into that aspect. Practically speaking, it won't be a flat current. It will be something, a small increment current will be there, but it can be considered as a very negligible current. I can say there is small dependency that is even still will be observed in the saturation region. So basically, VDS term will come here, but that will be for a very practical scenario that will try to observe in terms of certain demonstration examples. There I can just show that how exactly it is going to depend. But in basically speaking, I can say that in the saturation region, there is no dependency of drain to source voltage on the current. So that's what can be seen over here in terms of triode versus saturation region. So that's how the current equation looks. And like I told, even though if you increase VDS beyond a certain potential, there is no effect on the ID. That's what has been mentioned over here. Yeah. So that's about this particular theoretical aspect. So now let us try to get into some sort of laboratory demonstrations where we'll try to ensure how exactly we're going to see the incremental voltages with respect to the drain current in terms of both saturation region as well as the triode region. So I'm going to start my tool. So let's try to look into this. So try to install these softwares in your laptop so that you can get into getting used to all these things. Let us try to open up the cadence and let us try to plot some VDS versus ID and or ID versus VDS and ID versus VGS in a simple manner. Although you might have done this in your laboratory sessions, but I'm going to show you certain things over here. So in the meantime, let me just try to get you one particular thing. Yeah. So basically, if I just see here, I was talking about one particular aspect on the body effect, or rather this I'll talk about a little bit later. Let us first try to get into these particular things. So let us try to open up the tool. Just wanted to show you how the body voltage or the potential of the body, if I'm considering an NMOS, if I do not connect it to the same potential as that of source, how it is going to vary. So that I'm going to show you. So this is basically how you open up the tool Virtuoso ampersand if you write. So you're going to open up the Virtuoso tool, and basically once you do that, this particular dialog box will open, and I'll go to the file, and then I'll first go to the new library. I'm going to create a new library. So here I can say that NMOS demo, something like that. I'm going to use a term called as attached to an existing technology library, and I say OK. When I do that, it will open up this option. GPDK90 is what you're supposed to choose, and say OK. So that means whatever the library that you created has been now successfully attached to a particular technology node GPDK90. That is generic process development kit of 90 nanometer technology. Then again go to the file, new, cell view. Now go to the library which you have created right now. NMOS demo 1 is the library that you created right now. Go there, and here I'm going to give my cell name which I want to give. So I'm going to give the cell name also as NMOS demo. Let's say OK. When I do that, a black GUI is going to open. So this is where you're going to draw your schematic. So to draw the schematics, certain rule. So I'll just try to give you the glimpse of how to draw the schematics altogether in the next session. But right now, let us try to demonstrate what I already have. So I'll take up a simple example. So next, that is basically in the next session, I'm going to totally give you an attention towards how to start the cadence and how to work on to the cadence, how to draw the things, everything I'm going to give you. But right now, I have already some particular demos ready with me. So let us try to get into that, and I'll try to show you that particular aspect. So I have some set of demos already present with me. Let's go with that. So this is basically an NMOS where I am connecting the gate to source voltage. So you can see over here, this is the structure of my NMOS. Gate to source voltage is being applied over here, and there is a VDS is also being applied. So this is my drain terminal, this is my gate terminal, and this is my source terminal. And there is a body voltage which usually we connect this way. This usually connected to the source, but I'm taking a simple VBS also. So now let us try to remove that, and I'll connect that particular body also to the source. So I'm just trying to give you a glimpse of ID versus VDS over here. Only simple drain versus drain current versus the drain to source voltage and gate to source voltage. Nothing more than that. Simple demonstration. In the next session, I'll try to show you why this has to be connected and how exactly these all symbols and everything has to be connected and how exactly to work onto these things. So I'll just go into the launch EDL. Because I have taken the voltages as a parameters, so I'll just click, I'll just say right click, copy from cell view. These two voltages will come, and I'm going to apply some voltage as 900 millivolt for both of them, and then I'll go to the analysis. I'll go to choose. I'm going to do the DC analysis, and I'm going to say save DC hysteresis operating point, sorry, DC operating point, and then say component parameter. The moment I click on the component parameter, select component will open. Click on this. So here I want to choose a particular voltage for which I'm going to plot the drain current. So this is the VGS voltage I'm going to choose. The moment I click on the VGS, this component parameter will open. You choose this particular VDC DC voltage and say OK. And then that particular analysis wing will be here. You have to give the start voltage from 0 to, let's say, 1.5 volt. That means I'm going to plot ID versus VDS right from 0 to 1.5 volt. So that's what I say OK. And when I do that, if you come back to this particular ADE environment, you can see that particular analysis has been attached over here. Now I need to say that what is that you want to plot. Basically, I want to plot the current. So go to the outputs to be plotted, select on the design. So my drain current will be here exactly at the drain side. So always remember, whenever you want to plot the current, you have to choose the nodes whenever you want to plot the voltages, you have to choose the wires or the supplies. So now I want to plot the current. So I'll choose this particular node, the red colored node. I click on this, and if you see, a marking has been coming over here. And then again, I go back to my ADE window. You can see NMO/D. What is NMO? NMO is basically the instance name of my MOSFET. MOSFET by default, its name has been taken as NMO, NM0. And D indicates that particular terminal that I have chosen. I'll say plot and save. Let's say if hopefully everything goes good, it should give me a graph. And I click on this run option, it runs. There you go. So this has given a graph. I'll just make it large, and I'll try to bring this axis right from 0 rather than from the negative axis. I'll scale it to manually. I'll start with 0, so that this is how my graph looks. I'll also try to change the background from, yeah, I'll try to change the width of this thing. I'll make it as thick. Yeah, there you go. So this is basically how my VGS versus ID graph looks. So this is here, you can see up to a particular voltage, the current won't be flowing. And after a particular value of current, maybe somewhere over here, you can see there is a small glitch that is coming over here around some 133 volts, something like this. Yeah. So here, from here onwards, the current starts to flow. That is basically it says that the MOSFET is going to turn on after a particular value of voltage. That is nothing but my threshold voltage. Now you may be asking, how do I figure out the threshold voltage? Is it that I should come over here and see on the graph? I can do that as well, but just here, looking over here, sometimes you may not be getting an exact value. I'll tell you how to get an exact value, but before that, let's try to plot one more graph, which is basically the ID versus VDS. Now I have already taken the analysis part, which is my DC analysis, and I have chosen the drain current. Now here I chose VGS voltage, and that's how you got VGS versus ID. Now this time I need to choose VDS. So that's mean I have to go to again the analysis portion, which I can do it over here also, or I can double click on this also. I'll go here, choose the analysis. Now remove this component parameter and select on the component. Now this time choose VDS and choose the DC voltage and say OK. And this will be here. And again, let these, the sweep range would be from 0 to 1.5. I'm not choosing the sweep type. Sweep type is the thing, but there are 3 sweep types: linear, logarithm, atomic. I'm just retaining it as an automatic, just not to have any complexities involved. So I'm just taking it as automatic. I'll talk about that sometime later. Analysis is DC. The only thing is now you have chosen the component name as V2. If you can see over here, V2 indicates VDC. And I say OK. And yeah. So now the drain current is chosen because I have already chosen that ID versus, now this time it is VDC. So let's try to run. Hopefully we should be able to get that particular graph of ID versus, there you go. Again, let me just change the axis property so that the axis starts from 0 volt, 0 point. There you go. At a particular, up to a particular voltage of VDS, the current is rising linearly, and after a particular voltage, it has reached the saturation, and the current is not rising as much as that it should rise in the triode region, but it is almost a constant kind of thing that you can see over here. Almost constant, but like practically I was telling, there is a small increase if I just take an horizontal line by pressing H. So if I see here, if I take 2 horizontal lines, look at the difference. So if I just pick over here, there is a 1 point over here, and so if I say just the distance between these two, there's a 74 microampere of current between these two. So basically, in fact, I can say not 74. So this is at 74, this is at 60. So almost the difference is, if you can see over here, dy 14 microampere of current, small incremental current is there. So all, that's what I'm telling. for a practical scenario, there will be always a small current, but still I can consider it as a almost constant current. So this is basically how your ID versus VDS graph would look. Now let us try to figure out how exactly my threshold voltage, or when exactly the pinch off happens, or when exactly the saturation is going to enter. So entirely all those analysis, let us try to understand. So before that, let's see here. Let us try to mark some more portion over here. Let's assume somewhere over here, I can say that I can consider after exactly this particular voltage, the current is rising very, very slowly. That means I can say this particular value of current is that, or this value of the voltage is that particular voltage in which the MOSFET is going to enter into a saturation region. But how do I exactly figure out at what particular voltage the MOSFET enters into saturation region? So for that, there is something called as dummy DC analysis. That means you go to this analysis and I do not choose any component parameter. I'll just say save DC operating point. I say okay, and then plotting mode, I'll just say it as append rather than replace, because what is happening here, if I just keep on telling the append replace, it will replace the older graph. So before that, let me just plot VDS versus, sorry, VGS versus ID. That also let me just plot it. Let me have both the graphs ready with me. Okay, it plotted here only. So let me just send this graph to new window. Yeah. So that's my VDS versus, sorry, VGS versus ID. So this is my VGS versus ID. Let me have all the graphs with me. So here I need to figure out what is the threshold voltage, and here I need to find out what is the saturation voltage at which the MOSFET is going to enter into saturation region. So now let us try to do the dummy DC analysis. So like I was telling, to do the dummy DC analysis, I won't be selecting this component parameter. I'll just be doing simple DC analysis and say okay. And neither I'll be not plotting also anything. And I won't be plotting anything. I just simply analyze the thing and I'll run it. So once I run it, so let's minimize this particular thing. Once I run this, it has run it. So there is no error or warning over here. You can see over here. I can close this dialog box. Now to see or to ensure the parameters of threshold voltage or the saturation voltage, all these things, you have to go to the results. There's a direct there is a print option over here, and then there is a DC operating point. Click on this, it will reflect and it will direct it to this particular window. Click on this MOSFET. The moment you click on the MOSFET, it will display all the results or all the parameters that MOSFET is involved with. And if you see over here, come down, the VTH is 133.9 millivolts and VD SAT is 383.073 volt. That means the threshold voltage is 133.92. Let's see that. If I just see over here, I'll just use the key shortcut key as V. Somewhere exactly over here, the MOSFET starts to conduct, and up to this particular voltage, the current will be 0. So this is basically the threshold voltage, which I just saw it over here, right? And VDS sat, which is nothing but the voltage at which the saturation region starts, which is given by 383.073 millivolts, can be seen over here. So let me just somewhere over here. Yeah. So somewhere over here, I can double click on this. I can make it as 383 and I say okay, it will come over here. So somewhere over here, up to this particular point, I can say before this point, MOSFET is in its linear region, and after this point, MOSFET has entered into saturation region. So this is basically how my entire graphical analysis of ID versus VDS and ID versus VGS can be figured out with the help of dummy DC analysis, which I can see over here. And if you see over here, VBS, you have connected it to the source, because see, if you see over here, the body has been connected to the source and it is grounded. That's why VBS is also 0. So in the next session, we'll try to understand what this VBS, how if I vary, what is going to happen. And if you see now, there is something called as region 2 has been given. That means presently my MOSFET is in the saturation region. So that is the indication of that, because you already applied VDS as 0.9, VGS as 0.9. And if you figure out the equation of saturation region, that is VDS should be greater than VGS minus VT. So 0.9 is greater than 0.9 minus 133 or 0.133. So that it satisfies, and that's why region has been mentioned as 2. So that's what you can see, it has entered into region 2. And there are other parameters. If you see over here, what all these parameters, and you can see ID is 67.3 microampere. So what exactly that indicates, if you come over here, so it is going to indicate a particular value of current in which the MOSFET has entered into a deep saturation. So it is picking up a particular value of current after this voltage. After this voltage, somewhere over here, 67 something over here, it is picking up that particular value. Why it is picking up that particular value? Let's try to look into that. That exactly, see. So this is at exactly 900 millivolt. So what was your VDS voltage you applied? We applied 900 millivolt. So at exactly 900 millivolt, what is the current? 67.36, and that's what has been displayed over here, 67.36, because we have applied VDS as 900 millivolt. IDS or ID are one and the same, not to get confused. So like that, there are multiple parameters, and all the parameters, if you see over here in terms of, which are represented in terms of C, they represents the capacitances in one or the other way. So these are all the parasitic capacitance. Parasitic capacitance means they're all the inbuilt capacitance that we observed within the MOSFET. More onto this we'll deal with some other time, maybe in the subsequent session. But this is how we try to give you the glimpse of the drain current versus various voltages and how to get the parameters out of these entire things.